right, so we're talking about DurableServer and not Phoenix today. So if you want to hear about Phoenix, Stefan on the Phoenix team is giving a talk right after this, so I need to try to stay on time. He'll be on this track as well. So Stefan has effectively been the Phoenix team for well over the past year, so thank you, Stefan. And it has allowed me to go and do product work for the last year and build a few interesting libraries that we'll talk about today. So we're going to talk about actually 3 different libraries today. This is like a Steve Jobs, like 3 revolutionary new libraries in one. Surprise. But really this is open source libraries that we have extracted out of the sprites effort at Fly. So if you're not familiar with sprites, it's a API and platform for running sandboxes, and these sandboxes are like full Linux computers. They support checkpoint restore, so like you can let your Codex CLI or your OpenClaw or Clyde just go full ham, and if it messes something up, you can restore the entire file system, and that restore takes like a second to get back to where you were. So like apt packages, the entire file system, it's like Git for the entire runtime. So this is something that we've been working on for the last year. It kind of grew out of the Phoenix new effort to have like this infrastructure building block for sandboxes for your agenty things. And the way that works is it communicates with an Elixir and Phoenix API, so I'll just show that real quick. So behind the scenes, you can do like sprite list, and this is an API call that's going to list all my sprites, and I can do a sprite create like hello Elixir, and then in like half a second, I should be in a shell to that sprite. So this is now a full disposable, but also durable VM that I can keep around, and it shuts itself down the moment I exit out of this shell. So it has a sprite CLI, which is really just a client of the sprite API. So folks are using this as their like remote codecs or remote cloud code, but you can also use this to create your own agent platform. So we have lots of customers that are building through sprites for their customers, running OpenClaw and their own agents, and anytime you have untrusted code that you want to run, sprites can programmatically do that. So the CLI is just a consumer of the API that we'll talk about. So I'm going to exit that, and the only other thing I want to show, if the screen can, so we can do sprite list - watch. So we're going to talk a lot about like state replication, and we can see I have a lot of warm sprites here, but if I reconsole into that sprite I just created, we'll say, what was it, hello Elixir. We can see if this shows up. Yeah, so now at the top, the hello Elixir is running, so we're replicating state around the cluster for all of this compute that comes up when it needs to be, and then the moment it's not being used, we shut that sprite down, so you're not being charged for it, and we're not using that compute. So if I exit the shell, it should go back to warm. You can see it disappeared from here. So these things come up and go down very quickly, which means we have customers that are like managing fleets of these things. They send a bunch of requests, the compute is there, the requests are done, the compute goes away, and we have to replicate this information around to keep an ideal state of the world. So that's sprites, that's what we've been building. It's working pretty well. But it's geo-distributed. So a lot of the things I'm going to talk about today, you might be asking yourself, like, why not just use Postgres? So the answer is, like, just use Postgres. Like, Postgres is great. But in this specific case, sprites are running across the planet. So if this is, the backdrop is a world map that is like monotone. So I'm not sure if it's visible, but sprites are running like US East Coast, West Coast. We're running in Europe, we're running in Singapore and in Sydney. So that's where we're provisioning physical compute. And that's also where the API servers are running. So this is, you're looking at a Elixir cluster that spans the globe, single mesh. And the idea here is like if you provision compute like your own development environment, or you're provisioning in an OpenClaw for your customers, like you want that running close to the customer, especially if it's a shell on your laptop. You don't want the latency for every key press over SSH to be terrible, but you just want to run the compute close to the user. Like it makes sense, I think, intuitively for us, especially if we're running like desktop apps, talking to an agent, and the agent wants to run some bit of code and get a result. So we don't want to send everything back to North America to have that work. So part of this was like we didn't want to put a single giant like highly available Postgres in IAD or US East 1, because that's how part of the fly infrastructure historically has worked. And that's a single point of failure. And when you're building infrastructure, especially you're building for customers who have many customers, you want it to be highly available. So if we're running in Europe and our US East 1 or IAD goes down, we don't want to be able to not start sprites because we have one data center having problems. So the architecture of sprites was multi-region, and we wanted, one of the hard requirements was like if a region goes down, we still need to be available in the other regions. So part of that was leaning heavily on object storage. So sprites actually, the file system of each sprite is backed by a bucket. So the entire file system is stored effectively on S3. We have a local volume, it's like a write-through cache, so like hot blocks are still like very fast to access, but we're leaning very heavily on object storage for sprites themselves. And that was natural for us to then start building the Elixir and Phoenix API layer, also leaning on object storage, because like it's a rounding error as far as like, cost per operation. When you're putting an entire file system, 1 million of these things, we've created well over 1 million sprites at this point, so that's 1 million buckets. So throwing a bunch of durable data from the API layer into object storage is not even a rounding error for us. And object storage is also a boring utility. So part of leaning on object storage was like we had this requirement of like a sprite create should effectively never fail in a region. And that means that like we want to go with like the most boring thing possible. And while object storage is expensive, it's basically a utility at this point. Like you expect it to work. If S3 is down, the whole internet's probably broken at this point. So we lean on object storage not because like it's the best technology to like back a file system with, but because it's available and it's running pretty much everywhere and you expect it to work and it mostly just works. And it's really a utility, a commodity at this point. Like it doesn't even fit on a slide for the number of S3 compatible providers that exist in the world. We're using Tigris, tigrisdata.com. We're big fans of them. They run quite a bit of their infrastructure on fly, but they also run multi-region. So everywhere we're running to provision compute, we also have a nearby Tigris region that we're writing to. So the Tigris buckets are all co-located with the compute, which is what you want. But Amazon S3 is multi-region as well. And while we were building sprites, like part of these requirements was like always be available, like create should be as fast as possible. Like it shouldn't be like you're waiting a minute for your compute to come up. It should effectively be I can create this thing and have it execute code in like half a second. And along with that, like our goal wasn't to build this like durable server or a durable object type system. It was just like we started building with OTP, as everyone does. Like we had GenServers that we started. They hydrated themselves from a bucket where they stored their data periodically, and then this worked, but it became like incredibly kludgy. Like every new GenServer in the system that was responsible for like managing upgrades of an individual sprite was then just like JSON encoding some blob of state. Periodically, it was like setting a timer to persist itself, and it became kind of just this glue code everywhere that was ad hoc committed across the code base. So the goal wasn't to set out and make this library. The goal was just we were shipping code and it was working, but it was like messy. So really I came in and tried to like what sucked, I made not suck, and that turned into an interface that was like, oh, this is actually kind of like Elixir's version of durable objects, and it's working really well. So it was born out of making production code that was messy, like not messy, and it turned into like, oh wow, this is like generally really useful. So when we look at this idea of like durable, stateful applications, like we can check out products that exist. Like I think a lot of us have internalized like what this durable object idea is, because Cloudflare put out a proprietary JavaScript runtime called Durable Objects. And the idea, I think, is at the high level makes sense, right? You have this globally unique identifier, you send HTTP requests to it, compute starts on demand for that thing, and it's co-located to durable storage that is fast to access. And if you don't mind running on a proprietary runtime that you pay per operation, then maybe Cloudflare stateful serverless applications are a good fit. But I think this idea of like globally unique identifier, we instantiate some compute, we attach storage, and now you're running a stateful app, I think makes sense, right? And if you break down what it would look like to build something like that in the context of Beam, it's like these are the kind of the layers that we had built up in sprites over time, kind of this ball of mud. We basically implemented durable objects. So it was like a reverse implementation of like, oops, we made durable objects in Elixir. And if you break down like what does this look like to make something like what Cloudflare is doing in Elixir, like you need global uniqueness, and like we have that, right? We have that concept, it's a process registry. Like Erlang has global built in. And then like routing is like not just at the HTTP layer, like Cloudflare, but like how do you get a request or a message from the global identifier to the piece of compute running? Like for us, that's a solved problem. We have a process registry, we get the PID, we send it a message. So routing is like done, you don't even have to really solve it. And then as part of sprites, we had a lot of data we're replicating around the cluster, like is the sprite warm, is it running, how many sprites are running for this organization? Like what are the maximum allowed sprites that they can run at any time? So we had a lot of data that we're replicating around that needs to be immediately accessible. So like if you send a request from North America and your DurableServer is in Europe because that's where you're servicing most of your customers, we don't want to have to go across the world to see like, can we actually warm this sprite up? We want to be able to know at this point in time something about that process. So we're replicating metadata around the cluster, and this is familiar to most of us in the community because like Phoenix Tracker and Phoenix Presence is literally a process group with metadata. So these things are just like naturally like just there, these concepts fit. So then you throw storage on it, whether it's like backed by Postgres or object storage, and you throw storage onto a GenServer, put a process registry in front of it, and boom, you have durable objects. Like it's not a big lift. The only more complicated bits are like load balancing. So this is something like what the Cloudflare workers or a pass is going to give you is like, it's not just about starting a GenServer somewhere and hydrating it, is what which is what we were doing at Sprites initially, but then some of our stateful durable processes were running their own SQLite Lightstream databases, and I'll show an example of that, but we were actually doing heavy I/O work for a lot of these processes, and we wanted to limit the number of SQLite databases we're running per server because they're all writing to a local volume, and they're backed by Lightstream, which replicates back to object storage. Again, we write a lot of stuff to object storage, which is nice when you don't have to pay for it. But the idea was these things are CPU heavy and IO heavy, so we had to start basically writing our own load balancing of like when I start this process, I actually want to check on the cluster who is available to run it and pick the one doing the least work. So load balancing kind of necessarily needs to be part of the durable object story, and that's built into DurableServer because we literally wrote it first for sprites, and it was like, oh yeah, of course you would need this. But it was less an intuition of let's build durable objects in Elixir and more like product-led. Like, oh, of course we have to load balance because CPU is spiking. And then part of what we're doing with DurableServer is running our stateful processes per region. So we don't want to say like always have this running somewhere and then it gets restarted in North America when it should be in Europe where your customers are. So sticky placement is an idea that is built in and something that fell out of what we needed to do for sprites. And then the only thing to make this work when you're backing by object storage is S3 conditional writes. So S3 supports like compare and swap operations as of two-ish years ago. I don't know that all providers will, but I know that like Tigris Data and S3 support this. And the goal for our default backend, which is object storage, it was like minimal, we wanted the minimal coordination as possible. So the ability to start a process and make it globally unique requires some kind of global lock. And we can implement that in a lot of ways. We'll talk about another way later in the talk. But the idea was like S3 itself could be the lock because they support if match, and if match takes an E tag. So if you like list all the keys in a bucket, you get the key and an E tag, which is like a version. And then you can use S3 itself as a lock by just scanning over the key space. You basically do a dirty read, you get the E tag, and then the process when it starts up, it stamps itself, like its PID is like, I now own this. And it's gonna do an if match header to S3 and do a put. That's gonna fail with 409 conflict if you lost if you race someone else and they won. So we're using S3, which is somehow internally, all these providers are doing some level of coordination, consensus algorithms. Doesn't matter, S3 if match gives us what we need for a minimal lock to basically own that key in a bucket. And this is all to say, like, what does this look like? And it's just a boring GenServer looking thing, because that's all it is. So part of this DurableServer is like, it's just a library. So it's not like you should look at it as a way to like rebuild your entire application. It's just like you reach for a GenServer today, DurableServer is just something you would reach for. It just solves these pesky problems of like, please make sure this server is always running, make sure it's running in these regions only, or have it run until it actually sets itself down, and how do we route to it? Like, it's just solving these small set of problems, these boring problems that you don't have to solve, but you would reach for it like any other OTP thing, right? It's not a huge framework, it's just this small library that allows you to build these bigger systems with. So it's just a GenServer with a few extra callbacks. One is dump state, and one is load state. So you have to have the ability to say, like, here's what I'm going to write to durable storage. It's not going to be the whole process state, right? You have lots of ephemeral state in your GenServers. You have monitors. Like, all these things don't need persisted, but you do need to hydrate the process on init from your durable state, and then as state changes, you can dump that state back to storage. And then it's just regular process callbacks, except a lot of our tagged tuples return this extra argument or tuple element, like a permanent true. So if I want to always have my counter running somewhere on the cluster, I can say permanent true, and this thing will always be started somewhere with its state. And then we also have version migration. So like load state, you can see takes a version. So as you're persisting these things and changing code, you then will have to necessarily migrate your data from one version to the next, and we force you to specify the current version to use, and the callback takes the version to avoid the footgun of having new state and not migrating. And then there's a bunch of things built in, like the process can permanently crash. So if we try to start it X number of times, if you didn't take care of some of these migrations and your process crashes with a match error, we won't just perpetually drive your S3 bill up by trying to do a get and a put 1,000,000 times over a day, which could be a whole talk, right? Like, I don't know if folks are like me, like if you're using Sentry or anything, like Elixir's ability to like overwhelm these upstream providers and like blow up your monthly allotment is amazing. Like, I don't think like most people in other platforms have this problem where like the system continues to like, it crashes, the thing restarts, and then like you'll find out in like one day of the month you've exhausted your Sentry error billing because like things like, alerts were firing, but the app was working. Like it just kept working even though it was failing 1,000 times a second. So anyway, we have built-in safeguards in DurableServer it monitors crash history. It will leave something permanently stopped until the programmer explicitly tries to restart it. And we'll see an example of that as well. But it should be this boring GenServer interface. And the other cool thing about this process group with metadata idea was it can export any metadata about itself at any time. So if we wanted to add our DurableServer counter, we wanted to say, like, you know what, anywhere on the cluster should be able to see the current count without going across the network or across the world to ask the process, hey, what's your current count? So your init can export metadata, and then anytime you experience a side effect like increment, it can also export its new metadata, which is going to be arbitrary map of data. And then that will be available to any node on the cluster to be read at any time. And what it looks like to start these things is, again, just like starting a dynamic supervisor start child. Like, again, it should be this like boring low-level thing for you to build your greater application with. So you start a DurableServer supervisor and your supervision tree, and then you call start child, and then you interact with it like anything else, except now that process is discoverable anywhere. Like DurableServer supervisor lookup will work on any node. You get the PID back in addition to the metadata that it last replicated about itself. And another library that fell out of this effort was a new process group and process registry. So we'll talk about this at the end, but Phoenix Tracker and Phoenix Presence is a process group with metadata. but it has no global unique process registry equivalent. So part of this effort internally to DurableServer, we had like a private process group and distributed process registry that eventually it was like, oh, this could just be a library. So we extracted it to a library called group, and it's supposed to have a boring name because, again, it's just like this boring process group and registry built into one. And the only, I think, really interesting thing about this is, one, it's highly scalable, but also it has the ability to monitor and effectively subscribe to key spaces as folks register or join or leave process groups. So you can have integration with your DurableServer, but in general, you can just program around events in the system. Anyone coming or leaving a chat room, you can just monitor that and subscribe and get events as things happen. So let's see an example of that. So there was our hello world. I'm going to increase the font here. So I have that counter loaded, and we have ensure started child, which is like, if this is never started before, start it. If it's starting somewhere, just return it. So I'm going to run that, and we can see that we have a process and the current metadata with the current count. So this was already running because I already created this. So ensure started just said, yep, here it is. Its current metadata is 1, and then I can interact with this thing like any other process. So I'm going to call that PID and tell it to increment. But before I do that, I actually want to subscribe to somewhere in my history I should have. There we go. So I want to subscribe to any event on the process group. I could do counter, my counter, or I could just say, so this could be my counter to get the specific, I can't type, the specific data about that counter, or I can just say / and subscribe to any counter in the system. And now my process in this shell is going to receive events. It's empty right now, but I can then do a GenServer call on that process. And I'm going to say increment. And if I flush again, we can see that we had a group event for the process re-registered itself, and we have the new metadata as 2. And we also get the previous metadata, which can be handy to say like what changed. And this is going to, right, this looks simple, but this is going to work across the cluster, across the world, right? We're deployed, all the way across the planet. Everyone that's monitoring that key space would have gotten these events if they're connected. And then if we hop over to production, a production shell with a ridiculously long node name here. So there's probably a whole nother talk, but sprites is running itself as a peer node in Erlang. So it's like running a VM inside the VM or alongside the VM to allow us to do hot upgrades and hot blue-green upgrades. But in any case, this node name is really long. So if you pardon the line break here, oops, I'm going to crash iTerm and reopen it. This is all a covert, hold on, this talk is a covert sale for tmux, because like, oh no, all my shells, but this actually I think is still running. Let's see, is it still running? Minus, yeah, this is still alive, so haha, tmux, terminal multiplexer, check it out. Yeah, woo, that's right. Yeah, iTerm crashes every other day for me, but it's fine. Okay, group monitor for my org tracker. So in production, I'm going to monitor just my org tracker because there's thousands of them running right now, and I don't want to leak customer information. So that org tracker 23430 that's my key for my org tracker, which is a DurableServer and sprites that monitors my sprites that are running, enforces rate limits, has my paid information to know how much I can run at once, and I'm going to subscribe to data about that. And these things, the org trackers mostly just run and chill unless you call them. So to experience like state change or side effect, I'm just going to move this thing across the planet. So if we go to production here, we'll see if it loads. Okay, let me blow up the text here. So this is the production dashboard for my org tracker DurableServer, and yeah, it's showing up. So there's no dashboard built into DurableServer, but it does have public interfaces that you can just tell any agent, given this public interface, build me a DurableServer dashboard, and this is what you get. So you can get information about the key, look it up, and then I can see like the crash history is stored alongside the DurableServer. So in this case, it crashed with a timeout at some point, 20 days ago, cool. So we're keeping crash history, and that's what we're using to determine if something is permanently failed that requires like a human intervention. And you can get the current storage state and the current running process state. But what I'm gonna do in this case is I'm gonna rehome this process from North America. It's running in Virginia. I'm gonna move it closer to us. So I'm gonna move this to, what's the closest region? Probably CDG, Paris. So I'm gonna move, already started. Okay, so there's a race there that we'll talk about. My DurableServer is permanent, so I just shut it down to move it, and then it was restarted on the local node that had it before I was able to start it in Paris. Let's see if I can get it to work. There it goes. Okay, so the race we saw was actually a good thing, right? Like I shut it down. I need to work on the rehoming code because we shut it down gracefully, which means it was eligible candidate to be restarted because it's permanent. And then IAD was like, that's my key, and it tried to restart it immediately. But we just shut it down and beat the other node from claiming it again. So now we move that across a planet. It's running in Paris, and we can call this thing like you did anywhere else on the cluster because it's identified by this key. So we should be able to see what happened here if I run flush. So this thing's now running in Paris, and again, I call it like I would call it like any other GenServer, and we can see that the subscription returned unregistered, so it shut down, it was in IAD, and then it registered itself back in IAD because DurableServer Lifecycle Manager was like, oh, this is available to start. And then I tried to rehome it again, it registered itself in IAD, and then it re-registered itself in CDG. So we're just putting into metadata in init, like where it's running, because it's just good to have for display purposes and to know where these things are. And by default, when you start an org tracker, we just start it as close as possible to the fly edge node that you came in on. So it makes sense that mine was in Virginia because that's where its first home was initially. But you can move these things around and pin them wherever you want. So now this thing is running in Paris, and we can actually see this probably will take a couple seconds. I'm going to do a sprite list here. So its SQLite database is started on demand, so the process is running, but it's not backed by its database yet. So the first time I run this, it's going to clone its database from local object storage, start Lightstream, and then service that request. Maybe. We'll see. Oh, there it goes. Okay, and now it's hot. And now I'm going to be able to service the request quickly. So there's some really interesting things we're doing with this org tracker DurableServer especially, one of which is on-demand distributed SQLite that we can call from anywhere in the cluster because we just route to that process that owns the SQLite database itself. So there was a little demo. We'll have another demo in a bit. Another feature that was required for sprites was isolated subclusters. So we're replicating all this information around, which is really nice, but most of our customers, whether it's an individual user or a customer servicing many customers, they're usually regional. So we don't want to replicate all data about organizations everywhere. One, because the public internet can only do so much, but two, because it's just expensive. So we have this idea and group of isolated subclusters. You can create any number of them, like tens of thousands. We have one per organization. And then any node that gets a request for an organization just subscribes or connects to the org cluster, and then we immediately replicate any metadata about organizations to just that node that cares about it. And then TTLs can be added there as well, which automatically disconnects itself from a subcluster if no process group or registries exist after that TTL. Otherwise, it bumps itself and it checks again. So this is hard requirement for sprites, not necessary for everybody, but very useful to have as just like a general purpose feature inside a process group or registry library. And this idea of always running somewhere means different things. So like our org trackers, we want to run close to the API requests that they service. So they're gonna run in some meta region like North America or Europe or Singapore. And we have like a broken app tracker. We have a few other Durable servers in this, but like one of the nice things with Durable server is you just start these things for like, I want to have a Slack bot that posts to the sprites channel every hour about like pool health and how many sprite creates we had. You just create a Durable server, you say it's permanent true, and then it started somewhere, and once an hour, that thing's running somewhere on the planet, just getting information and then calling the Slack API. So we have global singletons for like these simple use cases, but also for cases where it doesn't matter where they run. Like we're running Open SQLite. We have a job queue using SQLite with Open that just runs somewhere, again, backed by Lightstream. So this really interesting way to do jobs through a global singleton through Durable server, because like if we exhaust the concurrency limits of an individual Open SQLite, our next job queue can just be another Durable server that starts a totally separate queue as a just totally separate database, right? Because these things they don't have to just be packed into one database. So we're relying on object placement to always run somewhere, but in some cases, that somewhere is just a specific part of the world or a specific machine. And the callers, again, kind of mask this. Like instead of Durable server owning your app, it's just gonna be like a dynamic supervisor start child, except you'll have something like a Durable server supervisor ensure started child. So our Slack reporter in production looks like this. It just ensures that the thing is running somewhere on application start, and after that was run a single time, it'll be running somewhere on the cluster from here on out until it deletes itself or you delete it. And then routing, again, like instead of Durable server owning your whole app, it's just like boring Elixir code, right? Like the way we route to a org tracker is like hidden from the caller. So we have this track sprite which enforces rate limits. And internally, the call path is just gonna say, make sure that org tracker is running, get the PID, and also the metadata. And then we can determine from the metadata, should we even call this process? So like we hop into like a condition to say like, if the sprite is actually running already, then we know it's not rate limited because we allowed it previously. We can then check the metadata to say like, are the max active sprite IDs less than or greater than the maximum? If they are, we don't call the process, you're rate limited. And then we only say if it looks like you can actually go track this sprite, which means you're provisioning compute, we will call that central process. So we avoid the single process bottleneck, and you might be hopping across the data center, you might be going across countries, you might be going across the ocean, but we want to avoid that in the hot path, which is what this routing and metadata give us. And then load balancing is something you stop thinking about. So it's just a configuration. You can say, I want to run max children in my dynamic, or my Durable server supervisor. I can say the total number of Durable servers I'm going to run is 10,000. And then if I have heavy IO CPU bound things, I can limit the actual children, specific children, to a certain amount. So we load balance on limits, and we also load balance on, you can opt into, I only want to route if CPU is below some CPU average of 80%. We can load balance on memory as well, and max disk. So you're automatically, after a few configuration flags, we're going to spread the load for you and then start refusing placements on node candidates that go above these high water marks. And then for sticky placement, we're relying on that for kind of these SQLite Lightstream databases, especially because we want it to run in a meta region, but we also don't want to clone the database across a physical machine constantly on every restart. So we want to pin to a specific machine for a certain amount of time, just because it's faster and cheaper for us to have that on the local volume. And then after a time-gated window of, let's say, 10 seconds, we will fall back, we will fail over to the fly region for this machine, and then we could stop there, and then it would only ever place in a region. And otherwise, we could say after that time-gated window of 20 more seconds, we could fall back and place it anywhere. So you have these knobs to control where nodes get placed, pin them to specific machines, and it's just environment variables that are going to be, that information is replicated around the lifecycle manager internally to identify eligible nodes for placement. And at this point, you're probably thinking like, this looks great, but like object storage is boring, but it's also very expensive. And it's easy for me to say it's a rounding error for sprites because it is, but in the case of your application that isn't backing file systems by object storage, it can add up. And I think object storage is actually cheaper than I expected for this use case, but it is definitely a consideration. So I started looking into a behavior for the DurableServer backend when we decided to open source this. And we haven't written a Postgres one today, but it's on my list, but I think someone could probably do it in a day. But this is where the other open source library comes in. So part of sprites, unrelated to DurableServer, was a distributed key value store. So we have effectively just cached information about sprites, like whether they're warm, as they go from cold or warm to stopped. The fly infrastructure periodically will just take a sprite that has a reserved block of memory, and it will claim that memory for other infrastructure. So we have to know when these things happen, and the fly API tells us. And internally, then we just want to mark that in a key value store of, from any node on the cluster, I can look up the current sprite state, and it should be there in an eventually consistent way. So this is this is durable state, but outside of a process. We just want to have fast access that's not in memory about certain things. So we had this small key value store. EKV was available on Hex, which is awesome. So it's an eventually consistent key value store, but Elixir key value store. And we wrote this thing. It was working great. And it's eventually consistent. Messages, it writes to SQLite. It has no runtime dependencies. I mean, SQLite is pulled in and precompiled, but it has no runtime dependencies. And mostly just works as long as you can write to disk. And messages that are missed get caught up. And this was working great for us as this like sprite information key value store. And when I went to write the behavior for DurableServer storage backend, it was like, oh, I wonder if we can just use EKV for DurableServer. And a key value store is just what object storage is, right? Like a key value store, S3 is just like get, put, list objects. Like we already had the EKV with like get, put. We had scan, which is like scan over a key space it returns a stream. So like EKV already had all of the features we needed, except for the pesky like compare and swap if match header, right? Like how hard could that be to solve? And EKV also had subscriptions. So like every library I write in Elixir has to have like real-time notifications, because like of course. And you can subscribe to a key space in EKV. And anytime someone writes to that room or any room, you can then get events from EKV about the key being put or deleted. And again, here's a subscribe on an entire key space. So we were using this kind of thing heavily in sprites outside of DurableServer. And then I was like, well, what would it take to add compare and swap to EKV? And this is something that was easier than I thought. I won't like really go into it, but it's using effectively, I named it version, but effectively an E-tag, right? Every key has a version, and any node can do a stale read on a key and get its most recent-ish version, and then attempt to do a cast on that. Or you can also do a barrier read. You can just say like consistent true, and you're going to get a consistent read on that key. And with this interface, we would be able to support a backend in DurableServer that you're not paying per operation. As long as you have disk available, it's just going to work. And I implemented this with cast Paxos. So you can read the paper, but Paxos is very complicated. And cast Paxos is much simpler, even though it shares the name. But the only thing I want to call out is the authors of cast Paxos said that like we struggled with Paxos ourselves. We were not able to understand the complete protocol until after reading several simplified explanations and designing our own alternative protocol. a process that took almost a year. So in order to understand Paxos, the Cas-Paxos PhD smart folks, it took them a year to be like, oh, that's how Paxos works. So Cas-Paxos is a simplified protocol that fell out of them being like, this is way too complicated. And there's really not much to it. The only reason I chose this is Cas-Paxos is, Cas stands for compare and swap, or compare and set, depending on the literature you read, but that's all we needed. So like S3 supports compare and swap, and that's like a very small subset of consensus and the way you would build like a distributed multi-writer thing. But for DurableServer, that's all we needed. So like the way Raft works is it replicates like a log of information, which allows you to build like full databases and have a history of operations. But Cas-Paxos is just replicating values, and basically that allows it to be leaderless. So this worked for sprites because we're running multi-region. Singapore has a high packet loss. Like in the evening in Singapore, sometimes we'll have nodes that like flap a little bit because like there's like more traffic there and packet loss goes up. So we wanted something that was good for basically no leader, so we could just always attempt a write from anywhere, and as long as you reach a quorum, that write commits. So EKB has opt-in Cas-Paxos, and it just works. We have a model checker that tells us a pretty good confidence that it works, but we'll see this at scale here. So I have a ride-sharing demo, and I don't know if I got my hand wave for, like, am I out of time, but we'll keep going unless someone drags me off stage. But so I'm running a DurableServer in, I think, like 5 regions here. How many nodes are we running? So yeah, we're running 9 nodes across North America and Europe. And this is running with the EKV backend. And if you ask LLM, like how many global, like I asked like back in the napkin, how many concurrent Uber rides are there across the planet at any given time? And it like did some web searching, and it told me about 500,000, which like passes the smell test. And that was what I targeted for this demo. So if we take the ride sharing example, like ride share is a lot of stateful, like where's the driver currently, where's the rider, like you're marrying up those two entities together, sending messages back and forth for like where each of the drivers are. And then when you claim a ride, you need to send messages back and forth between the user and driver. So there's like some really interesting ways that we could probably all intuit how we would model this just in OTP. So it was like, well, if we wanted to model this at Uber scale, let's just start 500,000 of these things. We could start 1 million. I think Jose and Jason have seen a video with me running 1 million, but it takes a while to spin all those up. So 500,000 is what I'm running now. So we have 500,000 riders, we have 50,000 drivers running various regions across the planet right now. And if I go to my rider page here, I can go like claim a ride. So this is all like actually running processes backed by EKV and DurableServer. And you can imagine like if you build this in a GenServer, you would have a rider and it would be married up to a process that's representing the driver. And you need these things to be globally identified, especially if they crash or go down, you need to reconnect to them. So it's like, it makes sense that you would want this to be at least identifiable globally. There's gonna be some state that you wanna know, where was the driver last, where are they now, are they available for rides? And then once you are assigned a driver, you have some push notifications that are going to the user's device about where the driver is, and then it's sending coordinates periodically from the driver. That goes up to a process somewhere, right? And then that thing broadcasts or pushes to the user, here's my current geo-coordinate, so the UI updates where it's at. So I'm simulating this, but like these are all processes running, and like the map simulates where they are, but like these are all messages going back and forth. So if I go hail a ride here, we've got 6,000 drivers in the Madrid region, and we're gonna hail a ride, and that matched me up with it said ride requested, the driver matched, and you can see he's now on his way. But this is like, the process is ticking, sending updates, and that's making it to the rider, and then sending notifications to the live view. The driver was confirmed, I'm now in the ride, and I get my ride progress, right? And these are all like sending messages through send, through group metadata, and it's updating my device, which is the live view. So we just see I'm getting close to the conference venue here, destination closed, driver release, and now that's released. So this is all ephemeral state, but then can be durable, right? So this durable server for the rider and driver could be periodically persisting the state we care about, communicating with the payment gateways, doing all that, but there's all of this ephemeral state, like notifications being sent. How do you route from user to driver? How do you recover if those things get disconnected or that process crashes? Like you need all of these kind of features. And like all of us without DurableServer can intuit how we would just have demoed the same thing, right? It's just a GenServer process send. But the other cool thing is I have the riders aren't permanent, but I have the drivers as permanent true. So riders are started on demand. Drivers seem like something you would always want to be running somewhere if the driver, drivers are the thing that is required for someone to claim a ride. So I'm going to go bounce one of these servers, and we'll see if EKV backend is able to restart them. So we'll say if I restart one of these things, we'll pick a region. It doesn't really matter. Maybe LHR. Yeah, I have a couple nodes there. So we're running subsets of these 50,000 drivers in different regions. So if I kill LHR, roughly half of the drivers in that region should go down. And since they're stopping gracefully, okay, that was quick. I was gonna say it might take a while, but so we have 12,000 drivers that just dropped off the planet because that node bounced. If the node had died before gracefully writing its state, we do have orphan claiming built in. After a heartbeat plus some time, the processes would have got claimed as well. But you can see now we're restarting those drivers on the available nodes. EKV multi-region is able to do like 8,000 writes a second, but DurableServer start actually does 2 writes. So we're starting like a couple thousand of these a second currently. And the lifecycle manager on all of the nodes is basically scanning the key space and saying, am I eligible to start this thing? And those drivers are then being claimed only in those regions that the sticky placement is configured on. If they were permanent true and we didn't configure them with sticky placement, they would just be started globally somewhere. But obviously, for this use case, we would want them started where the driver actually was previously. And after another minute here, we'll have our 50,006 back up and running, and we could provision 1 million of these things if we wanted to. It would just take a while to actually get them all seated. And these things, like I said, several thousand writes a second is no problem. And whether it's object storage or EKV, Postgres could probably do a very good job as well if you're running these things in one region. So it's definitely something that's on my list. I just haven't had a production need for it yet. And we can see now we're provisioning writers. Let's see how many I can get here. So 455,000. See if I'm being honest. Okay, that was another 4,000 after a second or two. So okay. So yeah, performance is pretty good. And again, this is going across the Atlantic. So if you ran EKV, if you run an EKV cluster in just one data center, you're going to effectively get a lot more throughput than that. But again, the use case for us was something multi-region that can survive availability going down, so avoiding leader election. So then last thing I want to talk about here is like if you're familiar with Phoenix PubSub and Phoenix Presence, like group may look much like PubSub shaped thing. So I'm still exploring like what it looks like to effectively replace like Phoenix Presence with group internally. Because it turns out like Phoenix Presence has served us well, but it's backed by a CRDT. It just turns out that like Phoenix Presence, I implemented, it's my fault, with a CRDT, and we didn't actually need a CRDT. So there's like a lot of extra complexity and performance trade-offs there that just don't need to be there. Because Phoenix Presence uses an OR SWAT, and that SWAT acronym is like observe remove set without tombstones. Observe remove set, and it turns out like the observe remove part, you have to observe if someone has removed keys from the set. Like it turns out that the presence use case, you never need to observe the removes, which means the whole point of the CRDT is invalidated, except we are still observing all the removes. So there's like all this work, CPU bound work that we do in presence And it's scaled well enough that we just haven't been bothered to fix it. And by we, I mean me, over the last 10 years. But group effectively, I feel like gives me what I would have rewritten presence with, and we kind of did it by accident with the process registry and with metadata, and we just replicate on demand as things happen. We effectively can replace presence with something much better. Then you also get isolated subclusters. You get the subscription notifications that can work. So there's work involved with like, how do we do this in a backwards compatible way and just internally use group with Phoenix presence, or is there something that we need to do to expose more group-like interfaces with like a major Phoenix pub sub version? So there's some level of figuring out things that we need to do, but I think the group work is great to use on its own, and I think it will also pay a lot of dividends for Phoenix pub sub itself. So that's all I have. I'm gonna leave with what I left with the ElixirConf US, where like I feel like something like DurableServer is gonna let us go build the future of like what this agenty world looks like, right? You can imagine a DurableServer for an agent on the server that is like the entire message history for like the Phoenix new agent is just in GenServer state. We persist it periodically to Postgres. And this is something that you can now have agents on demand running with their internal conversation state. If you're backing it by object storage or EKV or Postgres, it's something that's gonna scale super well and just be running when it needs to. So check it out, and it will be on Hex within the next 30 minutes. So thank you.